In this tutorial, I will show you how to plot root locus plots. These are very common in controls classes, and you will have to do them plenty of times, but the good thing is they're very easy once you get used to them. So we'll jump straight into an example in order to learn how to do these. So let's say we have g of s is equal to s plus 3 over s squared minus s minus 2. So this is a transfer function that we're going to work with. The first step is to find the poles and zeros. So in order to do this, we're going to simplify this a bit. S plus 3. This becomes s minus 2 times s plus 1. So a pole is a value of s which makes the denominator have a value of 0, and a 0 is a value of s which gives the numerator a value of 0. So this is fairly simple for this problem. So zeros. In this case we only have 1. So s plus 3 is equal to 0 when s is equal to negative 3. And the pole, we have 2, so s minus 2 is equal to 0 at s is equal to 2, and s plus 1 is equal to 0 when s is equal to negative 1. So now that we have the poles and the zeros, we will draw these on the real imaginary axis. So this is our real axis, and this is our imaginary axis. Zeros are symbolized with a circle, and poles are symbolized with an X. So we have a 0 at negative 3, and we have a pole at 2, and another pole at negative 1. So once we've done this first step, we will move on to the second step, which is to plot the locus on the real axis. So in order to do this correctly, we have to use the first rule, which says that the locus exists on the real axis to the left of an odd number of poles and zeros. So what that means is we check every location and see how many poles and zeros we are to the left of. So for example, at this location we're to the left of 0 poles and 0 zeros. At this location we're to the left of 1 pole. So the root locus exists on the real axis between these 2 points. And at this location we're to the left of 2 poles, so the root locus does not exist on the real axis. And at this location we're to the left of 2 poles and 1 0, which adds up to 3. So the root locus does exist on the real axis at this location. And this goes on to infinity. Once we've drawn the root locus on the real axis, we have to determine if we have to find the asymptote angle. It is only necessary to find the asymptote angle when the number of poles is greater than the number of zeros. And that is the case here. So we will have to find the asymptote angles. So in order to do that, we need 2 pieces of information which can be used from the following equations. So we need the location of where the asymptote angles meet, which is found using s is equal to the sum of the poles minus the sum of the zeros over the number of poles minus the number of zeros. And in our problem, this is equal to 2 minus 1 minus negative 3 over 2 poles minus 1 0. This is equal to 4. So this is the location where the asymptote angles meet. And the second piece of information we need is the value of these angles. So theta is equal to 180 over number of poles minus the number of zeros. This is equal to 180 over 2 minus 1, which is equal to 180. So the asymptote angles meet at s is equal to 4, and the angle at which they meet at is 180 degrees. So we will draw the root locus plot again. So we have a pole at 2, and we have a pole at negative 1, and we have a 0 at negative 3. And we said that the asymptote angles meet at 4, and the asymptote angles is 180 degrees, which is on the real axis. So we will draw the root locus again. And once we've found the asymptote angles, we have to determine, using the second rule, if we are done. So we have to say that the locus, the poles either meet up with a 0 or go to an asymptote. In this case, we have two poles meeting up and a 0 going to infinity. It's an asymptote. So this has not fulfilled the requirements. So what has to happen is that this pole has to break out, break back in, and connect with the 0. This pole has to break back out and break back in, and go to infinity. So these points are called the break and breakaway points, and they will be found using the following equation, where S is equal to the numerator of the transfer function times the derivative of the denominator of the transfer function minus the numerator, the derivative of the numerator, times the denominator. And this is equal to 0. So we will be solving this equation. Let's put in all the important pieces of information first. So this was s plus 3, and the denominator is s, the derivative is 2s minus 1 minus the numerator, derivative of the numerator, which is 1. The denominator is s squared minus s minus 2, which is equal to 0. So once you can use your calculator to do this, and this comes up to be s squared plus 6s minus 1, which is equal to 0. So you solve this using your calculator, and you get the following results. You get s is equal to 0.16 and negative 6.16. So these are the break-in and breakaway points. So they will be located here, 0.16, and here, negative 6.16. So as we said, this pole has to break out and break back in and connect to the pole 0. So it goes like this. And this pole has to break out and break back in and go to infinity, like this. So this is our root locus. This is what it's going to look like. And in order to make sure we've done it correctly, we have to use the last two rules. So the first rule is the number of branches is equal to the number of poles. So the branches, it looks like you have to do it like this. You have to determine for every pole, you have to determine where it goes. So as we said, is the pole goes to either a 0 or an asymptote. So this pole goes from here, breaks back out, connects to the 0. It doesn't matter which pole goes to the 0 as long as one of them does. And the second branch is where this pole goes to infinity. So that's 2 branches, 2 poles. And the last rule is that the root locus is always symmetric about the real axis. And this root locus is symmetric about the real axis. So all the rules have been completed. So this is the final root locus. All the rest of the root locuses can be solved in this manner using the same equations. And this is it, pretty much.